Thanks very much, Michael, and thanks everybody for joining. And I'm going to find this an interesting experience, not being able to actually see the audience. I was observing to Michael that I don't see the Zoom chat box on the interface since I'm sharing my screen, so I don't get to see the chat stream on Zoom, but I have got the Slack channel open on my desktop. So if you want to ask a question in the middle, then the best way that you're going to attract my attention is probably to send it to the Slack channel rather than to the Zoom channel. Otherwise, if you want to ask a question, you can always wait till the end. But if you want to catch my attention during the talk, that's going to be the best way. Right. So I was asked to talk about something without any specific brief, and I have interpreted that to mean that I can give you my my feelings about what planning needs to focus on in the immediate short term. These are problems that have arisen for us in various application areas that we're interested in, and have highlighted some of the things that we consider to be weaknesses of the current technology, and problems that we are actively searching for solutions to ourselves. And I thought, well, this is a great opportunity to get a whole bunch of other people maybe interested in trying to solve these problems too, so that I can steal their solutions and use them in our work. So these are problems that I offer to you in order that I can benefit from your insights. And I'm going to put them into a context of some of the work that's been done in planning in the past, but also into the framework of what I think planning is about. So let's start with a very straightforward problem. This is a somewhat dressed up problem, or a disguised problem, from that is actually one we're interested in solving, but this version of it obviously is a more whimsical version. So the idea is that we've got a collection of decorators that are going to have to paint a collection of walls, and the walls have to be painted through some sequence of coats of paint that depends on the specific wall. So each wall has its own sequence of coats of paint that need to be applied to it, and the decorators can move between the walls in order to paint them as they arrive, or once they've arrived at the wall, they can then start painting that wall. So this is a very simple problem. Let me show you what happens if we run a planner on an example. So let me first of all give you a quick view of what a very simple version of this domain looks like. So this is the simplest PDL version of the domain. So we have an action to paint a wall and an action that allows decorators to move between walls. That's it. And this is a non-temporal domain, so we're using the simplest possible formulation. I have a quite large example of a problem here. This has 50 walls in it, and a handful of decorators, 4 decorators, and some colors that have to be painted. So that gives you some feel for the problem. So let's run FF on that. FF makes short work of it, solves it, gives us a solution, and if we run competition, we'd be very happy with that, and we'd give on and say, yes, FF solved it very fast, everything's good. We might also consider solving it with LPG. So I'm going to try LPG on the same problem, and LPG comes up with a different solution. There we go, that's another solution. And you might say, well, this looks like it's a slightly better quality solution because its duration was 102. We can see that the last action is nearer the is earlier than it was in the FF solution. That went on to 139. So this might be a better quality solution. So if we were actually seeking to supply this solution to people, we might say, well, maybe LPG is the way to go rather than FF. But again, in a competition, we maybe say LPG did slightly better. It solved it fast and gave us a slightly better quality solution. So that's probably good enough. Let me show you what happens if I run another planner on it. So this offers a first solution that's got a make span of 59 and ends up with a solution that's make span 44. Now, clearly that is much better than the solution of FF, which you remember was 130 odd steps long, 139 steps long, or even LPG. And a crucial thing is, once you start actually scrutinizing the solutions, you realize that the quality of these solutions is very, very different. So in particular, if we look at the FF solution, it uses 140 steps to solve the problem, and 137 of them use the same decorator. So we have 4 decorators, but 137 of the actions in our 140-step plan are carried out by 1 decorator. The other decorators basically do nothing. LPG does slightly better. 96 actions are given to 1 decorator and all the rest are shared out. 145 actions in total, but the busy decorator is doing 96 actions. Whereas the alternative that I showed you there manages to split the work up so that the 4 decorators are essentially all doing about 40 odd steps. So they're all equally busy. Now, clearly, a good solution is going to make use of all of the resources. So this is an example where if we care about the solution, if we actually intend to execute the solution, then it really matters whether the solution is at least acceptable. Not necessarily optimal. I don't know whether that solution that I showed you was optimal, but at least we need an acceptable solution. And this has become very clear to us in looking at applications. Once you start providing solutions to planning problems to people who are actually going to exploit those solutions, who actually care about those solutions being executed, either by themselves, by teams of people, or by automatic machinery, you have to be able to stand the scrutiny of the plan so that it can at least live up to the basic quality of being sensible. If you have 4 resources, but you solve the problem by only using 1 of those resources, then nobody is going to take seriously the solutions you're offering. They're going to ask first question, why are you not using the other resources? And if you can't answer that question successfully, then the rest of the opportunity to deploy your solutions is lost. Of course, in real context, we need plans that are not only able to provide the simple propositional solutions that we saw there, but temporal and numeric solutions, and they need to be able to manage the interaction between the periods of time during which the action is executing and the numeric values that these actions are going to be manipulated. Just to highlight, what you're seeing here is the driller's cabin on a rig. So this is the driller, and of course the driller, if they're presented with a plan, they don't care what clever technology went on behind the planner and the plan. All they care about is what's going to actually happen on their rig. They are not going to take any nonsense, and they certainly aren't going to waste time scrutinizing plans that they don't trust. They're going to immediately abandon those plans and resort to following the experience that they know and have used to solve problems in the past. On the right-hand side, you can actually see the solution that we've been deploying on rigs in, well, actually now several places around the world. And this part on the left, which is labeled plan, is a plan that's actually constructed by a PDDL planner. So this is an actual PDDL plan. It's actually being executed. What you see on the right is the execution context, which the driller can be using to monitor the execution of this plan. But basically on the left-hand side, you see a part of a plan that is being generated or has been generated by a PDDL planner. And this is running on a rig. So this is the sort of screen that the driller gets to see when they're using this tool. Okay, so this is the first challenge that I am putting out as an important challenge for planners and the planning technology, is that we have to be able to produce plans that are of good quality. And that, of course, is nothing new, but one of the things that we have tended to fail to focus on as we've moved towards evaluation through competitions is whether the plans, all of the plans that are being produced by competing planners, are actually reasonable plans, or whether they're nonsense plans that just happen to solve the problem. Are they using the resources that are available to them efficiently, Do they respect the plan metrics? Are they actually generating plans that users would want rather than solutions to the problems that are at least as good as the other solutions that are being offered by other planners? This is an important part of the evaluation of what we offer as a technology. Okay, now what I'd like to do is to turn to considering planning as optimization and thinking about optimization more generally. And that's important because of the challenge that I just raised. If we're interested in trying to solve planning as a problem which respects the metric, then clearly one of the things we've got to confront is what is the optimization part of the problem that we're trying to solve. Thank you, Alison. Okay, so this is the optimization problem, the generic form of an optimization problem. We have to minimize some function of our vector of decision variables. So x underscore here is the vector of decision variables. I'm going to assume for the moment this is a finite vector, a bounded finite vector, or fixed finite vector of variables. Each variable has its own domain of possible values. And what we're going to ask is, what is the minimum value that f can take, which is a function to some real range, given that the constraints, which in this case are going to be represented by this function g and this bound c, this collection of constraints must be satisfied for the collection of bindings for this decision variable vector x. Okay, so this is the classic form of an optimization problem. Remember that the dimension of c need not be the same as the dimension of x. There are some number of constraints, typically m constraints and n variables. So these two vectors need not be of the same length, but basically this is the form of our optimization problem. And we will say that any vector of decision values that sits inside our domains is that actually satisfies the constraints is a feasible solution. So we're interested in a feasible solution that is minimizing for this function f. That's what we're interested in. Of course, these constraints might more generally not be bound constraints. They might be logical constraints. So I've used here bound constraints as a shorthand. You should see this as a representation of a collection of different kinds of constraints, some of which might be bound constraints, some of which might be logical constraints or other kinds of constraints. Okay, so this is the form of the problem that is considered. And of course, if f and g are linear functions under decision variables and numeric variables, then we can use the classic linear programming methods to solve this kind of problem very efficiently. So certainly some forms of optimization problems are well understood and can be solved very straightforwardly. If we go beyond linear functions and start asking about nonlinear functions, well, we still have some methods that can be appropriate for us. So there is the classic Lagrangian method, where we introduce a Lagrangian multiplier and use that to help us to minimize this function by combining the constraints and a Lagrangian multiplier to allow us to focus on minimizing a single expression, including the constraints. But we do require f and g here to be twice differentiable functions for it to really work for us. And if we have that satisfied, there are other approaches that might also work. For example, barrier functions offer a way to satisfy these kinds of optimization problems inside convex constraint boundaries. So these find a feasible solution and then push that feasible solution towards the boundaries of the constraint area that they enclose. So this is a series of methods that work very well if we're talking about numerical optimization, but they don't work very well if we're looking at discontinuous functions and non-numeric domains. Discontinuous functions are essentially constraints that occur when we've got disjunctions. So when we face problems with some kind of disjunction in them, we will either model them with a function that represents some kind of step function, or a step function itself can be modeled by using a disjunction. So these are somehow the same thing. And you can see that here, because here's our disjunction. We're saying if X satisfies one constraint, we will return a value 0. And if it satisfies the complementary constraint, then we'll return the value 1. And so this is where the disjunction is encoded in the definition of this function. And you can see that written more explicitly here. So clearly that's one way that we can express this kind of function. If we have a problem that has finite domain variables, so domains that have a finite fixed range of possible values, then they will always involve disjunctions, because the way that we will need to express the fact that those variables can take one of those values is by essentially saying it must be the first value or the second or the first value. So if variables effectively directly introduce the disjunction for it. And of course, one of the simplest, purest forms of this kind of simple constraint problem, which involves these finite domains, is a Sudoku puzzle where every cell must contain one value out of the range 1 to 9. So the fact that these are numeric values is irrelevant. They could be letters, they could be names, they could be any discrete collection of 9 possible values. And what we're asking is that each row and column and each of these 3 by 3 squares contain 9 different values. So each of the values must appear exactly once in each row, column, and subsquare. So we could take a problem like that and treat it as an optimization problem. In fact, in this case, there isn't really a cost associated with the challenges, is really the feasibility part of the problem, finding a feasible solution. And we can describe this kind of problem in many different formulations. So there are lots of technologies that we might apply to solve a problem of this sort. For example, we could encode it as an integer program, or we can solve it using a constraint satisfaction program. So there are different ways. Sorry, the drilling is not actually in my area, despite the fact that you might hear drilling. I don't know where it's coming from. It's not from my area. Okay, so here's the constraints that we're interested in looking at. So we've got a constraint that the ith row, jth column is going to be represented by this value Cij. That value is going to be a variable to find values to. The value is going to come from the domain more than 9. So we're basically asking, what is the right binding for each of these variables? And the constraints are going to say things like, for each row, k, the number of different values we will get if we consider all of the ij values on that row must be exactly 9. So there must be 9 values in the row k. And similarly for columns, and then similarly for entries that are different, we must have those entries are different in the subsquares, and so on. So this is how we're going to encode this. And if I show you an encoding written in alternative forms, here is an example of a particular kind of constraint language for writing this problem. So here we can see that I've specified the values that form the domain. These are the variables that correspond to the 9 rows and 9 columns that make up that grid. These are the constraints that specify all rows, columns, and subsquares must contain different values, 9 different values. And then here are the clues that we were given in the original grid. So these must be satisfied. These are the original values. And we can ask a constraint solver to satisfy a problem of this sort. This is an integer program version of the same problem. So here you can see those clues specified up here. I've slightly renumbered the squares. This starts at 0, 0 and goes down to 8, 8, whereas here I numbered from 1, 1 to 9, 9. But the constraints are the same. And here are the constraints that say, well, so in order to explain that, let me just show you that what we're going to do for an integer LP encoding is we're going to use xijk to be a variable that is 1 if row I column j contains value k and 0 otherwise. So look back at this encoding, you can see that I say x00, which is row and column 0, must contain exactly one of the values from 0 through to 8. I'm encoding these as 0 through to 8 instead of 1 through 9. But the same encoding essentially as the other. And that leads to a large number of constraints. Plus, I have to write down all the constraints that specify the contents of the cells and the bounds on these variables. And of course, finally, I need to specify that all these variables are integer variables in order to ensure that I get an integer solution. And if I try and solve that, let's ask what happens if I try and solve that. This is LP solve, which is not necessarily the most effective solver, but it's a reasonable solver. This is trying to solve that Sudoku puzzle using an integer program solution. What you can see down here is it's iterating many times, and so far it hasn't been able to solve it. I'm going to stop that because I don't think it will solve it in a reasonable amount of time. Let's just compare that with what happens if I run a CSP solver on the Sudoku, the same Sudoku puzzle. There is the solution immediately generated, and you can see here are the values that are being put into each of the cells. On the right, you can see values that might still plausibly lead to a solution. So they haven't been ruled out, but they are possible values. And you can see that in most cases here, there is only one possible value remaining. So actually we know that only this value will solve it. These others haven't yet been ruled out, but they would be ruled out if the solution were to continue to explore them. Okay, so that's our Sudoku puzzle. And what we've identified here is that although we can encode this same problem, this same puzzle in multiple ways, in this case I've shown you just 2 of the possible ways we can encode it, despite the fact that both of those have the solution in principle in their solution space, one of them was able to generate a solution incredibly quickly and the other is not solving the problem in a reasonable length of time. What that emphasizes is, again, something that we know very well, that different solution strategies have different strengths and weaknesses. We don't have the same performance from all of our tools. The challenge then that I offer is, how do you choose the solution strategy to match the structure of the problem? And what is it in the structure of the problem that allows you to identify which solution strategy is the right direction to go in? And better still, how can you do that automatically? So you don't place the burden of identifying the right solution strategy on the user, whose knowledge lies in their domain, not in the solution strategies that you're bringing to them. So how do you take a description of the domain given to you in a language that the user is happy to use and identify which is the right way to encode it and solve it? Okay, thinking now about planning, we can see planning in this same kind of framework. So we can say that our planning problems consist of some finite set of actions and some finite set of state variables, where our state is then just an assignment of values to those variables. And what we're interested in is actions that have a precondition that must be satisfied in this given assignment of values to the variable. So given one particular state, the precondition of an action must be satisfied if the action is to be applicable, and then it will update the state by assigning a new collection of values to some subset of the state variables. This is stuff that you're obviously very familiar with. So classical problem, we just have to find this sequence of states and the actions that link between them such that each action is applicable in the state that precedes it and yields the state that follows it. So that's our target. And if we think of planning as an optimization problem, at least one of the ways in which we might be interested in optimizing it is to find the smallest length plan. So we might be interested in trying to solve it for the smallest length plan, but equally we might be interested in solving it for the most efficient plan. As I pointed out earlier on with the decorators, we might be interested in sharing work equitably between the different resources that are available to solve our problem. We might have costs associated with choices that we make in our plan, and we really might care about choosing actions that achieve plans rather than necessarily short plans. So there are lots of different metrics that we might be interested in optimizing when we think of planning as an optimization problem. Once we think of a plan of a given length, we basically now have a classic optimization problem. We can formulate it in the form that I've been describing as minimize the value of in this case, the length of the plan or the metric applied to the plan, given the constraint that the plan must take us from our initial state to our goal state, satisfy the constraints. The only challenge that we have in framing planning in that standard classical optimization framework is that the value of the length of our plan, k, is something that we typically just don't know in advance. And as a consequence, we have to consider solving a family of optimization problems of the form that I previously described for differing values of k. And choosing the right value of k to find a plan is part of the challenge of the planning problem. So we end up with effectively either an iterative deepening scheme where we incrementally explore values of k, or else we generalize the problem of the problem that I described previously of optimization of a finite collection of variables into a dynamic optimization problem where you can add variables as you solve the problem. And either of those approaches leads us into a framework we're now able to talk about planning. I'm not going to really explore tools that might see planning in this framework other than planners themselves, but just so that we can see the relationship between planning and the problems that I've previously described. Okay, so what I'd like to do now is to frame some of the rest of the discussion that I want to pursue over the rest of this talk in terms of a framework that John Hooker at Carnegie Mellon has been exploring and promoting for the last couple of decades. And I consider this piece of work, or these many pieces of work that John Hooker has done, to be an amazing contribution to the science of optimization and the problems that we're all interested in solving, planning being only one of the application areas of the work that he's been doing. So I'm going to shamelessly steal from his ideas here and present them to you, but I should emphasize that the idea of thinking of optimization is absolutely John Hooker's idea and not mine. Okay, so John proposes that we should see optimization problems in terms of three contributing components, the first of which is search. Obviously, we are familiar with how search plays its role, inference, and relaxation. And I'm going to now look at how each of those three components plays a role in the approaches that we take to planning, and think a little bit about what the limitations might be on the ways that we exploit each of these three parts of the way that optimization problems can be tackled in our planning technology. So in search, if we think about these three optimization approaches, what search sets out to do is to branch the problem. And it does it by adding a new constraint. So if we start with our original problem, which was to minimize f given the constraint g, what we do is add a new constraint to that problem. So in this case, what I've done is to add this constraint g prime of x is less than or equal to c prime. So this is a single constraint. So this was a vector of constraints. That's why you can see the underscore under the c here. This is one new constraint that I've added to that collection. And over here, the alternative branch is that that constraint is not satisfied. In other words, that the negated constraint is satisfied. And this is what our search mechanisms always do. They always add a constraint. And on the face of it, that might seem strange because solving a constrained optimization problem is typically made harder by adding more constraints. So it seems odd that search is helping us to solve the problem by adding more constraints. And of course, the resolution of that apparent paradox is that when we choose the constraint to add here, we're choosing a constraint that will actually help us to make this problem on the left somewhat easier to solve by reducing the scope of the range of possible feasible solutions. So we're hoping that we will choose constraints that actually help us to make these problems easier to solve, even though we're constraining them. Now, of course, if we choose a constraint to add to an optimization problem, and we don't really have a clear idea of whether that constraint is a good constraint or not, there is a possibility that we're going to over-constrain the problem, and it will end up not having any feasible solution at all. And if that happens, then of course our search will have to revert to the alternative branch, now safe in the knowledge that given that the constraint we added led to an over-constrained problem, it must be that in fact the negative constraint is satisfied if there is a solution at all. If there is no feasible solution on either of these branches, then of course our original problem had no solution either. So this is basically telling us that we can find a solution on this branch, or else there must be a solution on this branch if there is one at all. If we do find a solution on this branch, we might be satisfied with that solution and simply decide that we're prepared to accept that solution. But alternatively, we could use that solution to give us a bound on the quality of the optimal solution to the overall problem. And in that case, we can add the new constraint that the solution that we're now looking for must beat the solution that we have found so far, and add that to our alternative branch of our solution space, or any alternative branches of our solution space, and attempt to solve in the context of that additional constraint. And of course, that pattern is known as branch and bound, and I'm sure most of you are familiar with that idea that you can add the bound to your solution structures and try to improve your solution. Okay, here's a classic problem. This is a language, but they can easily be reformulated in a constraint language. And the kind of branching that we might do in an example where we have to make a decision about what choice of constraint to add is that we might say, well, what we have here is a collection of people who live in different houses. The houses are numbered 1 to 5. The people live in them, they have pets, they have favorite drinks, they have different colored front doors. But we could make a decision that possibly the 5th house is the red house, or else the 5th house is not the red house. One of these two things must be true. Once we've made a decision that the 5th house is the red house, then things clearly are going to help to improve where what we know about the state of the problem. We can exploit this information. We'll see in a moment how we can exploit it, but basically adding that constraint gives us an opportunity to tighten what we know about the possible solutions of this problem. Let me show you again efforts at solving this. So first of all, I will show you actually the LP solution for this. So here is an integer program version of the problem, so you can see that we can write many of the constraints in integer program language in basically a fairly natural way. So the Englishman lives in the red house, the Spanish person lives has a dog, the greenhouse owner likes cocoa, and so on. So we have constraints of that form. Some of the constraints that involve disjunctions, so these constraints represent things like over here you can see that the greenhouse is immediately to the right of the ivory house. So that leads to constraints that involve pairs of that constraint. But anyway, you can see that you have these constraints on these various coloured houses and so on, and these can be expressed directly over here in terms of the constraints on these various variables. And these variables x1, x2, x3, x4 and so on are essentially dummy variables that we introduce to allow us to express disjunction. And they're going to be 0, 1 variables that will cover either the disjunction is true or it's false, and that will allow us to capture these constraints. And down here we have a need to impose an integer constraint in order to be able to force a solution to our problem. And this happens to be a problem that the integer program can solve very easily. So you can see here is the solution to that. It's decided which house each of these people live in and so on. And equally, I could have solved the problem using a CSP. So here's CSP. So here's the expression of that problem in the CSP language that I was using. So the houses are 1 to 5. Each of these variables must be a house. So the different colors, the different nationalities, the different cars, the different preferred drinks and the different animals. And here are the different constraints that I was given, 15 different constraints. And I can then simply solve that using my constraint solver, and out comes a solution, again, very fast. So in this particular instance, both of these technologies work perfectly well to solve it, but what you can see is that they are, amongst other things, using search. And just to see how much search they might be using, let's ask this solver to give us some statistics. So you can see it's actually made 136 search choices in trying to solve this problem. So it's done a lot of search across different possible choices in order to solve this problem. What about in planning? How do we use search in planning? Well, simply what we're looking at choosing an action to add to the plan. That's one of the most important choices that we make when we're searching for a solution to a planning problem. We will often branch on the ordering of actions. So having decided that we want to add a collection of actions to a plan, we might make a further choice about which order those actions are going to be applied in. And we might make choices over alternative bindings of variables in action schemas, depending on whether we are using grounded actions to build our plan, or partially grounded actions or non-grounded actions to form our plan. We might have to make choices about bindings as we build our structure of our plan. So you can see that there are many choices that we will cause our search engine in our planner to have to make and manage in the construction of a plan. Here's an interesting example of a problem that search is not very effective at solving in certain cases in our existing planning technology. Here is LPG tackling a logistics problem in which we've got a bunch of passengers that have to take taxis between different locations. So here's my taxi problem being solved by LPG, and you can see it solves it quite quickly. It comes up with a solution, and again, we might be quite satisfied with that solution. But one thing that is interesting about that solution, I'll show you the problem it's using to represent this. What we can see is we've got a collection of passengers, Joe, Nancy, Mel, and so on. And some of these passengers only become available at certain time points during the solution of this problem. So Joe is only interested in getting a taxi at time 12, and Nancy at time 5, and Fred at time 17, whereas Mel is happy to take a taxi straight away. And we also have a constraint that says that this particular street that connects two of the locations in our map is closed until time 10. And how does that affect our plan? Well, you'll notice that LPG chooses to pick up Mel, drive up one of the streets, and then sit there for 9 time units before the street opens so that other driving can carry on from that point. So there's a long gap in this plan, and you might ask whether that's a necessary gap or whether it's an artifact of the way that the planner has solved the problem. And I can show you that if I solve it using a different planner, there was an opportunity to do a whole bunch of activity before that time point. That time point didn't have to be a block on activity. But for LPG decided to simply leave a long gap between driving up this road with Mel on board and finally driving over this second street to its destination and dropping Mel off, having waited 9 time units for the road to open. Clearly not a very satisfactory solution from Mel's point of view, but also not a very satisfactory solution from the taxi company's point of view, because there's a long gap when nothing is happening, when drivers could be driving. There's only one part of the road network that's been closed, and yet the plan is paused whilst we're waiting for that road to open. The reason that this sort of thing happens is that our search techniques, and often, even though LPG is using a local search, a lot of its search is driven by a kind of forward search strategy. A lot of the search is facing a choice between, when we're looking at timed initial literals, these time points at which things become available to the planner, it faces a choice between advancing time to arrive at that next timed initial literal or not. And the problem is that very often the pressure on a planner to actually do something that appears to progress the plan means that advancing time and grabbing that next timed initial literal looks like a good thing to do, even though it's burning time that could have been spent doing other things. And it will often favor that in preference to starting some longer sequence of more complex activity that it doesn't immediately see will lead to a solution. So very often the timed initial literals can distract a planner into simply rushing through them and getting things over with before they progress to the point where they have a solution. So here's another challenge that is currently confounding some of the work that we're doing, which is to avoid the urge to do stuff just by advancing time to get things out of the way. But if you put on opposite pressure on the planner and say, try and wait, don't push forward to the next timed initial literal, try and do things in the gap, what you can find is that the planner will simply spend its effort and energy wasting time on trying to fill up the gap, just doing stuff. So the urge to procrastinate or the urge to delay is just as harmful to the quality of the plan as the urge to do things. Okay, is that comment about video quality aimed at me, Michael? Do you want me to try cutting my video?
Yes, if that's okay.
Let me see if that will help. Does that help? Okay, let's see. Okay, so one of the important components of a search-based part of the strategy for solving optimization problems is that when you fail with a search choice, so when the choice that you made leads to an over-constrained problem and one that can't be solved, the solver then has to explore the alternative choice, and that will mean backtracking. One of the things that we find hampers solution in searching for an optimization solution is, where do you backtrack to? Systematic backtracking means that we simply return to the most recent choice, and that will guarantee that we don't miss choices that would actually lead to a solution. But often it will mean that we end up spending an enormous amount of time searching in parts of the space where there simply is no solution to be found. Dependency-directed backtracking allows us to return to the choice that actually led to failure. And I'd like to show you another example of how that kind of problem arises, or what the symptoms of that kind of problem are. This is a problem that I've referred to in the past as a garden path problem. And it literally involves a garden path, but because the metaphor of being led up the garden path seemed amusing. So the problem that we have is we've got to mend a gate that's at the far end of the garden path. So somewhere far down the garden path, there's a gate. It needs to be mended. It's got two hinges that need to be bolted onto the wall. The bolts are in the shed. They're up at the start of the path, and there is a long number of steps that need to be followed to get the shed. So how do we go about solving this? Well, let's look at FF solving this. Let's see FF tackling this problem. So here is the, so I'm going to solve it. First of all, I'm going to use this version of the problem. So we have, in order to make the garden path itself long enough, I have to step with my left and right feet. I have to keep alternating steps. So I have a long path to follow, left, right, left, right, left, right, along the path. I can pick up the bolts so long as my left foot is still in the shed, and I can fix the gate once my left foot has reached the gate. That's the structure of this problem. And here is the problem that we're going to ask it to solve. We're going to put the gate 1,000 steps away. There are 2 bolts, 2 hinges. Okay, so and we need both hinges fixed. So that's the problem, and here's the solution by FF, and you can see that FF generates a solution to this problem, which involves a lot of steps because we have to do 1,000 left and 1,000 right foot steps. So there's a lot of steps, but it solves it very fast, and it only searches 2,000 states, which, given that the plan is 2,001 steps long, that's a pretty good search. It basically found the solution straight down the path it followed. It didn't make a mistake. However, I made things slightly easy for it. And the way that I made it easy is I allowed it to use the same bolt to fix both hinges. So you can see it's used bolt 2 on both hinge 1 and hinge 2. Supposing that I say you're not allowed to do that, when you use a bolt, it's gone. You can't use the same bolt twice. What is FF going to do? Well, of course, it races down to the garden gate, and then it suddenly realizes that it needed the other bolt. Fortunately, FF is very, very fast at searching a large number of states, but you can see that it has now searched 15,000 states to figure out that it actually needed to get the other bolt when it was at the shed. So there is no interesting search going on in here. It's simply because I've made it possible to alternate your feet in different orders in order to make sure there's plenty of redundant search in here. But basically, the mistake that FF made, of course, is to leave the shed with only 1 bolt. It thinks that it can use the 1 bolt to fix the 2 problems, even up until the very last moment when it actually uses the bolt and then discovers that it's no longer available to it to solve the problem of fixing the second hinge. And in order to backtrack, it tries every possible way of walking to the before it finally returns to the shed and tries picking up 2 bolts. And that, of course, leads to an extremely inefficient solution, or at least an extremely inefficient search for the solution in order to find the solution that is 1 step longer than the original solution. And it's quite obvious to a human that in order to fix the problem at the gate, you're going to need to pick up the 2 bolts. You don't need to consider whether different footwork along the path is going to give you a better solution to the gate fixing problem. You can see that those 2 things are independent of one another. But our planner doesn't see that difference, and it fails to backtrack to the crucial point where it needs to in order to make a different choice. So here's another challenge. How can we implement dependency-directed backtracking in planner search? It's been done in constraint satisfaction search. Constraint solvers are very good at attributing the blame for failure to the points in the search space where the choices were made that were bad. But most of our planners, many of our planners at least, are unable to perform that same dependency-directed backtracking. They typically end up doing fairly dumb backtracking, systematic backtracking, in order to try and solve these kinds of problems. How do we attribute failure to the right point in the search space in order to attribute the right point? And it's a problem that has certainly vexed us for a little while. Okay, I'm now going to move to the second part of the framework that John Hooker proposed, and this is the inference part of the framework. So inference adds explicit constraints to a problem that are actually implicit in the structure that we were given. So in particular, if we have our structure of our constraints g of x is less than or equal to c, and from it we can infer that g prime of x is less than or equal to some specific c prime for a specific single c prime, single constraint here, then we can add that constraint to our problem. In other words, a constraint that we know must be satisfied could be added to our problem. And again, this is somewhat mysterious. And one of the things that I find particularly interesting about Hooker's work is the way that problems that the techniques that seem to be the key to solving our problems all seem to be, on the face of it, rather weak and unhelpful. So search, adding constraints to problems that are already hard, seems like a strange step. Inference, adding a constraint that we can see must already be true to a problem, doesn't seem to be helping us. How is that making progress? However, it turns out that if you look at simplex, you can see that the simplex algorithm for solving linear programs is actually just a series of inference steps. Everything that the simplex algorithm does is simply to apply explicit inference to the collection of constraints that it's been given. It adds new constraints to the existing constraints. And even interior point methods that I mentioned earlier for solving these and for convex non-linear optimization problems, these methods are based on inference steps. You are inferring constraints on the structure of the problem and using those constraints to solve the problem. The same thing happens in Sudoku. When you solve a Sudoku puzzle, you basically do inference. So if I look at this Sudoku puzzle, one of the first things that I might notice is that this cell has a 1 and a 3 in its column already, and a 2 and a 4 in its row already, and a 6 in its row already. So this entry can't be 1, 2, 3, 4, or 6. It has a 5, a 7, and an 8 in the same square as it, so it can't be 5, 7, or 8. And that means that the only value that it can be is 9. That is implicit in the structure of the problem already. Some sense I already knew that this value was a 9. But nevertheless, putting 9 into that box is part of what you consider to be solving this problem. So despite the fact that saying this value must be a 9 is not saying anything we didn't know already, it's clear that making that inference is actually an important step towards solving the problem. A constraint solver can only really make use of inference if the results of the inference can actually be expressed in the language that the solver is able to use. So one of the things that makes inference challenging in many of our solvers is that the language that we have available to us to express the kinds of constraints that the solver reasons with is limited, and many of the things that we might be able to infer as human observers of the problem can't be directly expressed in the language of the solver. Fortunately, that inference that I just showed you can. This is easily expressible, that the constraint that entry is 9 is easily expressible in the language of the solver. But if I now point out that once I know this entry is 9, I can observe that the 1, 4, and 6 must sit in these other 3 cells, but 4 and 6 can't sit in this cell because of this row. So 4 and 6 must sit in these 2 cells, and that means that 1 must sit in this cell. Now that inference is slightly trickier because in order to express that 1 is here, I needed to go via a constraint that said 4 and 6 must be in these 2 cells. And language doesn't easily allow me to express that 4 and 6 must sit in these 2 cells. I don't really have the means to express that constraint conveniently in my language, or to then express the constraint that must lead the value over here to now be not the 4 and the 6, but the 1. So allowing this collection of constraints to be expressed depends on my solver having the means to express that constraint. If we had a sufficiently rich set of inference rules and a sufficiently rich language for expressing them in our solver, then actually Sudoku puzzles proper Sudoku puzzles can be solved without any such tool. You simply do inference and solve them directly by inference. And you can kind of see that when you look at a problem that you solve yourself, because you don't end up trying numbers out and then backtracking over them, certainly not over deep searches. You might try a single value and then backtrack over that single value, but you don't do deep searches. If I return to the CSP solver that I showed you a moment ago and ask how many searches did this do in solving its Sudoku puzzle, you can see it did 17 searches with 17 backtracks. So clearly this solver is not inference complete. It doesn't solve this problem by inference alone. It solves it using a combination of search and inference. It makes some guesses, it then has to backtrack as it gets those guesses wrong. So many of our solvers are going to be forced to use search as a substitute for the power of inference, but nevertheless, more powerful inference is going to give us a reduced search problem. How is inference used in planning? On the whole, I think that inference is the poor cousin in planning. We typically don't make use of inference very much. And when I was trying to identify where inference really arises in most planners, I identify a couple of places where I think it's typically used to some extent. Adding temporal constraints in a plan where we have temporal structures in our planner. So using simple temporal network type reasoning, and inference of actions that must be in a plan where we do landmark reasoning. Those are basically the two most significant places that I think we use inference in planning. And we don't often use inference in other places. Let me show you a problem where I think that there is scope for using inference that we currently don't exploit and we could do much better. This is a simple machine shop type problem. We've got a bunch of parts that have to be machined with tools, and those tools have to be cleaned through use of them. And the tools have to be turned on in order to use them, but off in order to safely clean them. So we have this plan that will involve turning the machines on, using them, turning them off, cleaning them, and so on. So there'll be these sequences of uses interspersed by cleaning actions, and turning on and off will be interleaved with that. So let's have a look at solving such a problem. Here's the encoding of that problem. So I'm using a temporal domain here, so I'm not going to be able to use FF on it, but I'm going to show you a couple of other possible planners. So here's turning the machine on, here's turning it off. We can move parts around, we can clear them away once they're machined. We can machine them once the surface is clean and the motor is on, and we can inspect them. We can do that whilst we're machining them. So in answer to the question about which CSP solver is that, that's just one that I wrote. It's nothing very special. There are lots of CSP solvers that would be able to do much the same thing. But yes, clearly mine doesn't have very powerful inference. That's certainly true. Okay, so let's solve this particular planning problem using, so this is a version of PopF that's doing this. So you can see it solves the problem quite efficiently in terms of time, but does it solve it efficiently in terms of activity? Well, not really. If you look at the very beginning of the plan, you'll notice that the very first thing that happens during time 0 is, amongst other things, that we turn on the slicer. And that's a problem because we haven't yet cleaned the surface for the slicer, so we then have to turn it off again. So we turned it on, but we end up turning it off again, and that then actually delays the point at which we can clean the surface because we had to wait for the motor to turn off before we were able to clean the surface. So we can't get cleaning until time 2, when we could have cleaned right away at time 0. It was a mistake to wait until time 2. So we've ended up being inefficient in this first sequence of actions. And in the light of the comment that I was making at the outset about the way that the solutions can be scrutinized by a human, you can see that the moment that you have a solution which in its first few steps is doing something stupid, turning a machine on and then off again unnecessarily, people will begin to doubt whether the technology is what they need to solve their problem. I can solve that problem. Actually, let me use this solver. So I can solve that problem in a different solver, different planning solver. So this is solving that problem, and this is a temporal planner that is solving this problem. And you can see that the solution quality is better. The last action starts at time 30 instead of at time, oh no, this was also at time 30. So actually the solution length is the same, but the solution quality is better because the actions that it's performing are nice and organized in a way that human would recognize as a valid and sensible solution. So it starts by, in parallel, cleaning the surfaces, moving the parts, turning on the tools, cutting the parts, inspecting them, clearing them away. And it does that in lockstep all the way through this plan. So clearly, this is a good quality plan, whereas the solution that PopX produced here was a poor quality plan, even though its make span turns out to be the same. It's exploiting the slack in part of the make span to uselessly turn this machine on and off, and that leads the solution to look stupid. This is a problem where we're cycling these cyclic actions, and the reason that we end up doing that is that the planner recognizes that the machine that's off needs to be turned on in order to complete a task later on, and it also knows that when the machine is on, it's going to need to be turned off in order to do other stuff. So it keeps recognizing that the machine needs to turn on and off, but it doesn't fully understand that it's going to need to do that multiple times. It doesn't understand that at all. It just keeps discovering that after it's turned it on, it will now have to turn it off. After it's turned it off, it will now have to turn it on. So it discovers that as it builds the plan, and the result of that is a poor heuristic estimate of the number of steps that are needed to solve the problem. And you can see that in the initial heuristic estimate here. Up here, PopF is recommending that there will be 46 action endpoints. So that's 23 actions, in fact, that it thinks the plan will consist of. But you can see there are a lot more than 23 actions here. There are more like 30 actions or so in the plan. So it's underestimated the number of actions by about 50%. And the consequence of that is that there is an opportunity for poor quality plans to be built. And we end up with this very frequent cycling of state being one of the typical problems in getting these cycling type domains. So a challenge, infer how many times you're going to need to do those repeating cycle patterns. So in this case, we know how many things need to be machined. We know that the machine has to be turned on and off each time one of those parts has to be machined. It shouldn't be that hard for our planners to work out that actually the machines will have to turn on and off as many times as there are parts to be machined. Shouldn't be that hard, but currently none of our planners do. And if we could infer the structure of that cycle, so where in the cycle do you turn the machine on, where do you turn it off, then you could perhaps build the plan using that cycle as part of the structure in the search. So maybe you could improve the way in which you build your plan from the outset. Okay, I'm going to move on to the third and final part of this framework, the relaxation part of the framework. So the relaxation part of the framework is I remind you, this is John Hooker's work. The relaxation is to remove constraints and arrive at a simpler problem. And again, this seems like a strange thing to do. So all three parts seem odd in their own ways. In relaxation, we're removing a constraint, which means the problem that we'll now solve actually isn't the problem we care about. Why would we care about solving a problem that is not constrained in the way that the true problem is? How is that going to help us? The answer to that is that very often the solution to the relaxed problem gives us, well, first of all, it definitely gives us a bound on the possible value of an optimal solution to the original problem. If we can solve the relaxed problem optimally, then we know that the solution to the original problem is certainly going to be no better than the solution to the relaxed problem. So that's a bound that we can exploit. But also, very often, and this in many ways is more important to us in planning, the relaxed solution can guide us to make good choices for our search branches. So how do we choose a constraint to add in our search? Very often the relaxation will give us a way of finding a good suggestion. So mixed integer programs are very often solved this way. Basically what you do is to relax the problem so you get rid of the integer constraints, you make the problem a continuous linear program, solve it as a linear program, and then you can use that as a guide to how to solve the original problem. So let me show you backtracking in our linear program here. So this was the integer version. If I relax it by getting rid of our integer constraints, then the constraint on the yellow and green houses that they must be adjacent to one another, that's this pair of constraints here, involves this decision variable x5. That's the constraint that is that's the variable that is the 1, 0 variable that decides whether the green house is left or right of the yellow house. If I solve that problem as a linear program rather than as an integer program, you can see that the solution that is generated is actually pretty good. Most of these variables are actually turning out to be integer variables, even though we've no longer constrained them to be. But the first point at which we find a non-integer value is, in fact, that very decision variable x5 that was used here. That variable we know must be a 0, 1 variable. That's what we need it to be. So a sensible way to branch on our search for a solution would be to say, given that if we solve the linear program as a continuous linear program, we end up with a non-integer value for x5, how about we add a constraint that says x5 really had better be either 0 or 1. And since this is 0.2, that's closer to 0. A good proposal would be to start by saying, let's make x5 0. Let's see what happens if we do that. And of course, what that will do is to make the problem slightly more constrained. We will be able to solve it, but still solve it as a linear program, because we still can add that constraint in the language of a linear program. And then we can use the solution to that slightly more constrained version of the problem to try and improve our solution finally towards an integer solution. And of course, those of you who are familiar with integer programming techniques will recognize that that is one of the techniques used in branch and bound search for an integer program solution. Okay, so how do we use relaxation in planning? Well, of course, relaxation has proved to be a very valuable tool in planning. We've used it a lot, and the key technique that it applies to is in reachability analysis and the use of that to build relaxed plan construction. So using a relaxed plan to solve our problem, by relaxing our original domain, we can arrive at a problem that's easier to solve, and it guides our solution by offering us helpful actions. And although the heuristic value that a relaxed plan gives us is important in guiding our, I believe that the helpful actions that the relaxed plan gives us are in fact the most important part of what comes out of the relaxed solutions for our planning problems. It's the narrowing of our first choice of action to a very small subset of actions that turns out to be one of the key contributions of the relaxed plan in narrowing our search space. Okay, so one way that we can view the relaxation of problems is as a projection. So when you remove a constraint, what you're effectively doing is projecting your original problem by projecting away one of those constraints. That's one projection. But an alternative projection is to look at any collection of constraints that's implied by the original collection of constraints. So any set of constraints implied by the original collection of constraints could be added as an inference to our problem, but we can also use it as a relaxation of our original problem. So we now replace our original constraint set with this relaxation of the constraints. And that relaxation is an easier problem because satisfying it does not imply that we've satisfied our original constraints. But nevertheless, anything that solves the original problem will solve this relaxation. And so this relaxation gives us the power that we expect from having solved a relaxed problem. So one of the observations that I'd like to make is that a lot of the planning domains that we look at have sub-problems in them that we recognize as problems that have been explored in their own right and for which very good solutions already exist. Route planning problems, scheduling problems, bin packing problems, knapsack packing problems. All of these are problems that we recognize appear in our planning problems, but very often they're tangled into our planning problems in ways that are not pure. We find them embedded with other constraints that we don't fully understand and that we don't recognize how they will adjust the constraints of these sub-problems. Nevertheless, we can guarantee that a solution to the complete planning problem must solve those sub-problems. If those sub-problems are embedded in our planning problem, then any solution to the planning problem must solve the embedded scheduling problem or bin packing problem or route planning problem, whatever it is. And therefore, if we treat those sub-problems as relaxations of the original problem and use good heuristics that we know will solve those sub-problems, we can actually exploit those as relaxations of our original planning problem and try to solve the original planning problem with the guidance of those relaxations. So another challenge, how do you identify those sub-problems and solve those relaxations in order to find helpful actions and possibly improved heuristics in our existing planning technology? How could we exploit these sub-problems as projection relaxations? Okay, I'm going to pretty much finish up there. I'm going to summarize the challenges that I've offered because this is, I think, a useful collection of things that might guide some of the ideas that you're looking at in your own research. These are problems that have arisen for us in very real application areas that we are trying to solve with more or less pressing urgency. So these are the 6 problems that I identified, summarized on one slide. And I think that I will not simply read them all to you because you can read them all perfectly well for yourselves. Instead, I will say I am happy now to answer any other questions that you might have.
Thank you very much, Derek.
Okay.
Very nice, very nice. Very nice talk. Many illustrations, excellent overview, and very challenging problems. You put planning in a nice perspectives with respect to the various main steps of inference and relaxation. It's not only matter of search.
Yes.
Many other things.
And I think that one of the interesting questions for the planning community sitting in that context of optimization solving is, are we really using all of the tools that are available to us as well as we can? I mean, I think that many of us see search as our key weapon for tackling planning problems, but often we neglect the power that inference and relaxation can offer us in also helping to solve these problems. So I think it's helpful. One of the reasons that I find Hooker's work so inspiring is that it reminds me constantly to go back and ask whether those parts of our armory are being fully exploited in tackling planning problems.
Yeah, you are fully right. There is an S in ICAPS. We have had scheduling right from the beginning.
Indeed, indeed.
But we kept the two apart. Either some people were doing scheduling or some people were doing planning. And the challenges and the perspectives you are putting right away for all of us is to work for the integration.
Yes, absolutely, absolutely. I wondered,
okay.
Eli, I wondered when you asked about drilling, whether it's actually maybe my fan that keeps coming on my laptop every so often. Maybe it's too close to the microphone and it's picking up the sound of my fan.
I think it might be that. Ben just asked a question.
Yeah.
He said, how might one define plan quality? He imagines it depends on the problem itself, and that you might have a strange quality of, you'll know it's good when you see it. Do you have any ideas how you might look at this in a domain-independent way?
So this is a really challenging problem for us, the plan quality problem. So one of the ways in which we are constantly challenged is in trying to tackle risk. One of the things that a lot of the domains that people are interested in us exploring are domains where one of the parameters that they care most about, one of the costs that they care most about, is risk. They know that they are exposed to risk. What they want to do is to manage that risk, but balance the cost of managing the risk against the rewards that they hope to gain from having risked that cost. So the question is, how do you balance risk against the other costs? And very often the plans that we are generating have not simply actions in them to reduce the risk, but also actions that might anticipate a failure of some future event and mitigate that future risk by providing a context in which the risk will be minimized when it finally emerges. So you put safety equipment on site, not because having safety equipment there reduces the risk of an event happening, but because it reduces the cost of the event once it happened. So you're simultaneously thinking about, how do I mitigate the risk happening? How do I prevent the risk from occurring? But also, how do I mitigate the cost of the risk if finally it does happen? Both of those things matter. Now the question is, how much are you prepared to spend on those kinds of activities? How much are you willing to spend on mitigation of risk? And the part of the difficulty for us, of course, is that people are very reluctant to put into concrete terms the precise trade-offs that they're willing to make between risks and costs. The true answer is, everybody would like to minimize their costs, but they acknowledge that they also don't want risks to be too bad. And too bad means, how much can they get away with within the frameworks of legal responsibilities and environmental responsibilities and risks of loss of the profits that they hope to make from whatever it is that they're exploiting. All of those things factor in, but it's extremely difficult for people to articulate that in concrete terms. So what we found is often necessary is to present a user with choices. So you offer them a kind of, I'm going to say Pareto front of choices. In fact, it typically won't be a Pareto front, because that would require us to actually optimize with respect to any of the given metrics that we're given. And we are usually unable to guarantee that we're optimizing, but we're at least trying to do well against those things. So we're optimizing, but not optimal against these different metrics. And what we offer is a collection of choices. And one of the things that we observe in having done that is that very often the way that people make those choices suggests that they have a non-linear, very lumpy representation of the trade-offs they're willing to make. They have certain points where they're very clear about how much they're prepared to spend of risk or cost, and other places where they basically are feeling their way, exploring solutions, trying to get a feel for what the solutions offer, but they can't articulate clearly what it is about the solutions that they like that are better than the solutions that they dislike. It's extremely difficult to get people to articulate that. And so I think that my answer to your question, how do you get these metrics, how do they get generated, is in practice, we can only write down metrics that are approximations of what users are actually caring about. And then we have to offer choices to the users so that they can bring to bear their human intuitions about parts of the domain model that they haven't been able to articulate, haven't been able to capture that perhaps they don't even want to try to articulate because it touches on legal constraints that they don't want to make explicit. And those things are then left to the human to resolve. And I think that that's really the only thing that we're currently able to do in these situations.
Can't you offer a collection of utility functions that are quite flexible and let them experiment with these functions?
Yes, so that is indeed what we try to do. We offer a collection. So again, another challenge is how many dimensions people are able to understand when you start exposing them to multidimensional spaces. So we find that although it's possible to offer, for example, projections of the spaces into different dimensions, very often the way that humans understand it is really two-dimensional. They can understand a trade-off between two things. And what you need to do is to find a sequence in which to present those trade-offs that help them to narrow down to the most important choices first, and then refine their choices as they progress. So you really want to say, well, here's the big choice between risk and cost. That's your first big choice. Now, after you've done that, maybe there's a choice about which skill level we apply to the teams that are involved, or something similar. So you kind of provide the big choices first and then focus on the smaller choices second, because you can't present all of those trade-offs in a meaningful way simultaneously. It's definitely one of the big challenges. There's some nice work that was done by Mark Giuliano in the space domain, looking at trade-offs between different kinds of metrics for space telescope activities. And he confronted this question of how do you present to scientists the choices between multiple different dimensions. And he ended up with the same kind of challenge, that a multi-dimensional space is very difficult to present to a user in a meaningful way. And he has some interesting ideas that we have exploited, but I think that it's still difficult to do that. And as I say, I think that one of the very significant challenges is that humans don't have the means to articulate these constraints very clearly for themselves, let alone for us. They have a lot of difficulty in writing down how they would compare two solutions for quality. They have intuitions that are often flawed, so they will think that they're taking into account risk, but when you press them and present them with specific examples, you realize that their intuitions about how they take into account risk are not matched by what they actually do when they're confronted with real choices. So often they are not even able to tell you what they really do. They only tell you what they think they do, and that's not the same thing.
So Ben has another question. No need to apologize for multiple questions. He asks, do you think we need more than just values to specify objective functions, such as causality, patterns in plans, or hierarchy, or etc.?
Okay, that's an interesting question. So, I mean, as far as our planners are concerned, we are currently only really able to deal with two possibilities. We can deal with logical constraints, so you can close down choices of solutions by adding constraints that rule out things that you don't want to happen. And you can alternatively put in cost functions, which ultimately will give you a single value for the optimal solution. I mean, there might be multiple solutions that offer that value, but there will basically be then a single dimension value on which you're measuring the different quality solutions. If you offer multi-objective functions, so you basically evaluate across multiple spaces, then you can't choose a unique solution. You basically then have to go back to the user and say, which of these do you prefer? This is the Pareto front, how do you like it? Which one do you want? So the human has to then provide the combinator that links those different solutions together and chooses the right, or those different costs together and chooses the right combination. But basically, we only have either that metric, simple metric mechanism, or constraints that close down choices in the envelope of possible solutions. And certainly adding constraints is an important part of what we need to be able to do and do well, ruling out choices of plans that visit parts of the space that we don't want them to visit. But that is nevertheless a hard constraint. I mean, it becomes a hard constraint. Of course, you can impose a cost on violating those constraints, allow them to become soft constraints, but then you just back to combining it as part of the cost function. So I think really we have a limited collection of tools for dealing with these kinds of evaluation of plans.
Now, we have time for one more quick question. Parisa asked, are there any works that merge learning with relaxations, i.e. learning which constraints are better to relax or more effective?
So I can't say that I'm aware of any work directly on learning of relaxations. What I can say is that Patrick and Jorg in particular, and some of the group of people that work around those two researchers have looked at what they've called de-relaxations of plans. So trying to reduce the amount of relaxation that they apply to a problem in order to try and improve the quality of the relaxation as a guide to solving the original problem. And I think that what that does is to refine the projections that we have currently been using in planning. What I think it doesn't do, and I think that there is an opportunity to really exploit, is this idea of projecting onto problems, sub-problems that we identify and know how to solve well. And I think that that's an underexplored area that really could be tackled. Whether learning can help us to do that, I don't know. That it's very difficult because I'm not sure whether you can do this in a truly generic way or whether really you're looking for techniques that will apply to classes of problems. And if you're looking for classes of solutions, I'm not sure how much data we've got that really gives us good ways to tackle learning. I'm not sure. I'm not aware of any good work in that area anyway.